Okay, hi everyone. Welcome to the presentation. At this point, we're going to talk about the electrical interface performance matrix that we work on it over the last, I believe, 6-7 years. It's a long, basically, list of participants, but unfortunately, there was a limitation of the only 3 names up front. No, all the credit goes to all the people who work on this activity over the last 6-7 years. Okay, let me start with what do we mean by die-to-die interface. Basically, the whole goal is to look at all the interfaces that are right now available on the market for connecting 2 different die on the same package. Objective of this work stream was basically to accurately identify a comprehensive list of relevant parameters with respect to the performance and functionality of the interface IP and come up with a common method that everybody can accept it and use those methods how to measure those parameters. Not only those parameters are important, the way that we are measuring and reporting it is also important. We believe that this framework is going to help us to continue the use of the different IP interface and enable basically the open chiplet ecosystem market that we are planning to have. But why do we need it, and what is that we believe that we need is a common method of, as I mentioned, parameter measurements and performance reporting in the electrical interface IP. And the reason that why do we need it is, first of all, it makes the ease of integration. You know what are you integrating. It reduces the development time because you get all those parameters ahead of time. It enables industry collaboration. Now you know the competitor or your vendor, what they are actually offering in terms of those IPs. And you can actually compare them and pick it based on what you need from the application perspective or a customer perspective. And also, if you're looking for interoperability, then this actually table or this report can give you this option that, hey, these 2 PHY are or these 2 interface IP are interop or not. And quality assurance, and also if they are compliant with each other or not, that's another use of this white paper or work stream work. Again, from another perspective, we believe these tools is essential tools for open chiplet economy. We believe if you want to have a successful open chiplet economy, you need to have a chiplet interface standard. You need to have a collaborative design platform and a verification method, and also interoperability test kits. By basically the table that I'm talking about, this is a very, very short version of it. The list of this table is long. It's more than 40 rows, which we cover 3 different basically category of the parameters. The first parameters are non-technical one, related to more legal. For example, if this standard is open or closed, or do you have to pay fee if you want to use this standard IP or not. Second set of the parameters are technical but not tied to the technology. For example, how many lanes do we have? Bow, for example, is 16 or 32. Just want to look at it. Is it clock forwarding or not? Something that is not related to the implementation. And the third category of the parameters are parameters that we are dealing with the measurement result. For example, how much power you're dissipating. And if you are reporting the power, how you have to measure those power, in what condition, and then report it. Basically, this is the common method of the measurement that we are talking about. I think always when I present this kind of slides, I ask audience, okay, any PHY that you hear, immediate question is, okay, how much is the bandwidth density? X gigabit per second per millimeter. The follow-up question is TX, RX, or TX and RX. You know, we are trying to avoid this discussion. When we say gigabit per second per millimeter, we know what we are talking about. Are we talking about TX only or RX only? As a background, as I mentioned, it's started in 2017. Boppy, I think he left the room, myself and Ramin. We start actually gathering some information, very short table about a couple of PHYs and try to compare them, how much is the reach, how much is their bandwidth, speed. And eventually we grow up that list. It became in 2021, 2022, a massive Excel file that I'm sure most of the people have seen it in the industry. And we compare more than 25 different available by that time, different PHYs on the market. Some of them are legacy, no more people using it, like OpenHBI and others, AX-Link. But we had them all. Again, the Excel sheet was kind of long, comparing them in different basically categories in terms of power, density, and architecture. But during that data collection phase, which was basically very, very helpful because everybody who had the IP had to come and present and fill out that form to validate the data. But we find out even among ourselves, we cannot actually agree on a method of measurement. Again, those examples that I mentioned still exist, and the worst one, which took us at least more than 10 sessions, was latency. How do we report latency? I think you're gonna see some slide about it in this presentation too. But last couple of years after 2022, we find out that this Excel sheet is getting to the point that we are making the judgment that, hey, which PHY is better, which PHY is the worst. But that was not our intention. We left that part to the user and whoever actually providing that PHY. And for this year, we are actually just providing an empty Excel sheet with the methods and how to basically measure those parameters that hopefully everybody can agree on it and use it. And eventually we get to a common platform that we can compare different PHYs based on our needs. Nothing again to do that we say, hey, Bo is better than UCIe or UCIe is better than Bo. That's not the intention of this work group.
Great, thanks Shahab for the intro. So as Shahab mentioned, we have written a white paper, but it's kind of unique in that there's an accompanying Excel that they go together as a pair. And to address the question before it's asked, it's in submission and review, just like the last one. It has not yet been published. When it is, it'll be up on the OCP website. So this is a snapshot of the Excel. Each row is a different parameter. As Shahab said, it's empty and you can fill it in. This is the first section he mentioned, which is a sort of qualitative. What type of signaling is it? What is the signaling type? What's the termination you're using? Is it a standard? How does it work in that sense? And so this is one section that can be filled out. And I'm not going to, I can't go through every one of these. We don't have time here. But each one of these rows in this Excel is accompanied by a section in the white paper that describes in text what this means when you're trying to decide differential versus single-ended signaling. Which one do you enter in your spreadsheet? What does that mean? I think most of us know, but we have a good explanation for that. What's single data rate, double data rate, QDR? What do those different clockings mean? There's text to describe all these. That's the white paper. But here's an example. One of them rows on that was logical link. So unidirectional or simplex link is just data that's transmitted from one chiplet to another. We had examples earlier of like a DAC that mostly unidirectional data, but a lot of the interfaces we think about, UCIe and bunch of wires, are often bidirectional or dual simplex, where you've got data that's going from one chiplet to the other, and you've got data that's coming back between them, and they're on separate lanes. So you have one transmit lane and one receive lane on your chiplet, dedicated wires. A third option here is dynamic bidirectional. If you were here earlier, I mentioned this is what doesn't exist right now in the Bo spec, but we're adding it to the Bo spec. It allows you to take a lane, and sometimes you're reading and sometimes you're writing, and that allows it, the same port can do one or the other. Instead of dedicating an entire set of ports to read and another entire set of ports to write, if you have asymmetric data flow, dynamic bidirectional half duplex is how all memories are built, DDR, LPDDR, everything, all the DRAMs out there, and the reason is to enable users to put whatever data they want. So that's a different type of logical link. And the fourth category here is full duplex on a single wire. That's simultaneous bidirectional. So that's both directions at the same time on a wire, different than the half duplex where you're either doing one direction or the other. And this is, let's say, a unique one that Eliyan at my company is doing, but is not as common. But we try to break it down this way so that when you're going through and saying, what kind of PHY am I describing, you can fill in the type that is applicable. lots of white paper text to describe all that. The second is more quantitative, so how many data lanes do you have? How many data wires? If it's single lane and signaling, those two would be the same, but if it's differential signaling, obviously you have 2 wires for every data lane. How many clocks do you have? Do you have any sidebands, which most of the data dies have, to reach around and help do initialization and stuff? And what is your speed per data lane that you're targeting? These are all quantitative descriptors, and we have examples for all those. This is a calculation example. In the back to the unidirectional simplex, if you have 1 wire and it's running at some speed, you know how much total data you're transmitting. If it's dual simplex or bidirectional, you have twice that data because you have a wire going one way and a wire coming back, and so on and so forth. So you can take the earlier qualitative definitions and apply them to quantitative, how much actual bandwidth is being transmitted between devices, and we can hopefully get away from the is it TX or RX or is it both when we are describing bandwidth between chips. The third, and this is a huge list here, but these are very much design specific now. Now we're not talking about a PHY type, but an actual implementation. So what's the bump information? What is the bump pitch and the bump arrangement? And of course, what is the beachfront? What is the depth? What is the total PHY area? How much is assigned towards data versus clocking, for example? These are all rows with, again, descriptions of how you fill them out. And then the last here are actual measurement-related parameters. So we have a whole section on latency and bit error rate and how you measure them and under what conditions, because again, as Shahab mentioned, the conditions, just a number by itself doesn't mean anything unless you know what conditions that was measured under. So here on for example, on the bump pitch, this is a typical, most of the data dies are staggered arrays like this, but they don't have to be. There's a lot of linear bump pitches out there. Most of the packaged ones are. So we modeled based on the half pitch, and that allows whether the PHY is arranged with a square, rectangular pitch, or staggered like this. You can use these parameters to describe your PHY, and you can use that to come up with the area and the beachfront size if this is the chip edge along the bottom. And so that in a consistent manner, people can describe different PHYs that are built on whether it's advanced packaging, 25 micron pitch, or standard packaging, 130 micron pitch. You can define it and in a consistent manner. And then last of these calculated parameters is latency and bit error rate. So a lot of discussion, a lot of confusion over how to do this in the industry over the years. We've drawn a very simple diagram here. If you're familiar with the UCIe spec, the serializer deserializer interface, think of it as the RDI level interface, and it's just a SerDes with a receiver and transmitter. And that is a latency number that is very interesting from a PHY latency standpoint. Most users are also interested in the sort of application, the FDI layer or higher that includes whatever packetization you're doing. If you have FAC or CRC like a UCIe requires, that latency inherently has some encoding and some decoding on the other side, so it's going to be more latency than just the PHY itself. So they're different numbers. An additional factor that complicates a latency discussion is it actually depends how fast you're running. So typically people quote their latency at the highest speed they can possibly run. That's great. All your serializing and deserializing are clocked at the highest clock rate. And that's going to be the smallest the number can be. So, but we added in a fixed data rate on the parallel side so that we can compare sort of more apples to apples of different PHYs using a fixed data rate and then also whatever their max data rate is. Those two numbers might be the same. It might be a gigahertz on the parallel side corresponds to 16 gig on the line rate, and those are the same numbers, but in a lot of higher bandwidth ones they're not. And this creates extra rows, but it allows more definition on the PHYs that is consistent. And then last, it's not so much a latency issue, but if you support retry and you're trying to figure out how long does it take if an error is detected to come back around and do it all again, we report the numbers for the latency on that and how we can get the bit error rate down. Okay, and I'm going to turn it over to you, James.
Thank you, Kevin and Shahab. So, yeah, I think there are two tables I want to present here. Mainly, I think one is like the calculation and the figure of merits or forms. So I think there are a few important parameters, I think, which you mostly calculated. I think from those measures, I think as mentioned in the previous slide, as you've seen. So I think one of them is talking about the power efficiency, which measure the energy I think, efficiency within the PHY. That typically a lower value, I think that's better. And then you have another unit bandwidth, right, which is gigabit per second that measure throughputs, and that high value better. And then you have power bandwidth densities in the that measure total power consumed to support a given bandwidth. So this is, and I want to higher that the better. And then I think it's the bandwidth edge density for the PHY, right? Which is measuring, I think, the throughput density at the edge of the PHY dial. So, and I want that is higher, the better. And then you have bandwidth area. Is way kind of correlation with the edge, and then this one measure more kind of across the entire die area. So instead of the edge, so same thing, that's the looking trying to get a higher value on that. And then the last two we have the figure of merits, right? Form one, which is the edge bandwidth densities. Which measure the balance between power efficiency and so edge density. So you kind of combine the previous two together. So the other one, this is kind of another higher one that indicate better overall PHY technology performance. The second form is the where you put the power efficiency relatively to your transmission distance. So that gives you the lower value, that better efficiency over the longer distance. So I think these are the important metrics that typically you want to calculate when measuring the overall performance. And then there one, I think across the industry, I think these are recommended minimum list of the parameters over the many of them that we look at. I think there's so many of them. I think we don't not all of them were applicable based on the use cases. But these are the most common one. I think they weigh generally. I think the high rule. I think that's why I think we put in the last slide. I think it's important. I think to pay attention. I think we have participants. I think in the group. I think recommend this from the industry standpoint. So I think the D2D. I think die to die spec. I think version. I think you have data length space. The PHY bandwidth. I think both, I think I put show lines and then the without show line, and then you have a reach, and then I think it's a power efficiency, something we have seen before, and then you need to know about the packaging type, the minimum bumpage, and then you have that I see earlier, and lastly, I think the least is the latency. I think that you it's very important. I think this is the minimum requirement. I think we looking for the manufacturer. I think I will be providing this information. So yeah, here's a longer list as Shahab mentioned earlier. I think all the participants. I think we have a list of people. I think that contributed to this white paper. So thanks to all the participants here. And lastly, we want to call for action. So we have weekly call on Tuesday at 9:30. We have a white paper, as Shahab mentioned again. So it is going to be available soon. So it's always submitted in OCP right, for review. So that's it. Thank you.
Sorry, I have two requests, if you don't mind. Sorry, I know we are almost one time left. If you have any PHY, please come to our meeting or at least use this white paper. Right now we are in the phase that we are using it internally, and some of the folks are using it and try to complete the list of this table and see how good or bad it is, the dry run format. But soon we're gonna get to the final release. We appreciate if your company has any PHY that you would like to check it, try it, and give us feedback. And second request is from those who are actually customer of those PHYs. Please force your vendor to use this Excel sheet and send it to you. Thanks. Sure, we will do that.
May I ask a question?
Sure.
Is it going to be the same spec or white paper for DDR5s also, for the parallel IOs?
Our intention was that any kind of PHY, you can use it and fill out the information. You know, we are trying to be as general as possible. I think even last time we had PCIe as one of the available PHYs for interface.
So DDR is going to be covered also?
If we are not gonna fill it in, you know, if you are a DDR vendor, feel free to use it and fill it in.
Thank you.
Thank you.
Thank you, Shahab, James, and Kevin.